Just try to see it, that I also see that it will be easy for move through the slides.
You open the slide now.
Yeah, is slide not open?
नहीं, slide show, मतलब complete slide, F5 you have to press perhaps.
Okay. But
has left the meeting. Yes. Huh? You go to slide mode. Okay. Okay, now it's okay. It's perfect. राजकुमार, आपको वॉइस वो करना है, खोलना है, वॉइस आपने बंद किया हुआ है, वॉइस अनम्यूट कीजिए।
किया था
हाँ ठीक है, नो इट्स ओके। हाँ अब आप
sorry for the disturbance, there was some call from...
No problem.
Okay, so these are the contents. I will be discussing basics of interferometry, then types of interferometers. I will also go for holographic interferometry, as this is a special type of interferometry which is generally not possible with other conventional techniques. Then we have developed some of the holographic optical element based interferometer. So I will discuss that interferometer, and finally I will also discuss digital holographic camera. That is a portable camera which works on the principle of digital holographic interferometry for non-custody testing applications. So before going, let us slightly introduce about CSIU. It is a constituent laboratory of CSIR, Council of Scientific and Industrial Research, and it was established in 1959 by Act of Parliament. At CSIO, we run research activity as well as HRD, and higher degree like MTech and PhD are provided through Academy of Scientific and Innovative Research, while diploma level program, which is market oriented, is provided by Industries Training Center, ISTC. So development of globally competitive technologies is the main thing, and this was moved to Chandigarh in 1967. Building was inaugurated by Dr. Zakir Hussain, then President of India. And in 1963, ISTC was inaugurated by Pandit Jawaharlal Nehru, the first Prime Minister of India. So mandate of CSI is research, design and development of scientific and industrial instruments for societal, strategic and high science applications. This is R&D structure of CSIU. So head of the institute is director, and director is supported by research council, an external body with renowned persons from industry and academia, and management council that is generally from within the CSIO and some expert from sister laboratories. Now CSI is divided into 5 verticals and 5 horizontals. So verticals are agrionics, which is generally based on pre-harvest and post-harvest agriculture related technologies, biomedical engineering, optical devices and systems, advanced materials and sensors. I think this is the photonics division, which is working in sensors and precision mechanical systems. Horizontals include ubiquitous analytical techniques. This is mainly working in the area of nanoscience and technology, computational instrumentation, human resource and development, knowledge management, and engineering services. And these are the groups within optical devices and systems division of CSIU. So we have optical design, optical fabrication, metrology, holography, thin film, optomechanical, and optoelectronics. And various technologies have been developed and successfully commercialized by our division. Few of these are head-up display for LCA Tejas. This is also developed for other variants and working on say naval version and Mark II also. Taxi landing lights for LCA and LINAC, this is for medical therapy. We have excellent facilities in the area of optical devices and systems. And I think these are best facility in civil sector for any of the lab in India. We have conventional optical grinding, polishing, all these facilities are there, conventional fabrication. Then we have recently added 5-axis CNC grinding machines, 6-axis CNC polishing machine. We have optical thin film coating plants, 3 plants are there. Then metrology, these commercial interferometers are there. This is Zygo. And this non-contact profilometer. And this trioptics system for say lens parameter measurements, focal length, radius, curvature, etc. Now coming to holography group. In holography group, we are working on say holography, interferometry, some diffraction related techniques. Yeah, these are interrelated, and we develop few technologies. Our current is digital holographic camera that I will describe all these techniques in coming slides. Holograph shearing interferometer, diffraction Lloyd mirror interferometer, slurring system for different applications, for even defense applications also. And this is laser lithotripsy that we developed with lenses for treatment of kidney stones. Now I will fluctuate some between diffraction and interference for few slides, just to make the thing more clear. So we can see that this razor blade, if we illuminate it with the light, we can see these fringes at its edges. And these fringes are, we call diffraction fringes. And what is diffraction? So according to one of the noted scientists, Arnold Sommerfeld, any deviation of light rays from rectilinear path which cannot be interpreted as reflection or refraction is called diffraction. So if say this is a point source and we put a knife edge there, it will generate a knife edge diffraction pattern like this. In this is shadow region, where this region where light is not directly going, and this is illuminated region where this DC beam, generally called geometrical light, is approaching, and also some light diffracted from the knife edge going, is generating knife edge diffraction pattern. Okay, so we can explain mainly with two theories. There are many theories, but two theories are widely used. These Fresnel-Kirchhoff diffraction theory and Young's boundary diffraction theory. In Fresnel-Kirchhoff theory, which is generally we are studying in most of the textbooks, every point within the aperture serves as a source of secondary wavelengths. These secondary wavelengths interfere for further propagation of the wave and for generation of diffraction patterns. But boundary diffraction wave theory says that when some diffracting aperture, let us go to previous slide. When some diffracting aperture is there, you can divide the whole field into two parts. One is geometrical light with directly propagating, means it's not interacting with the diffracting aperture. That is on a geometrical wave. And second, light interacts with the diffracting aperture, gets scattered from that. And that is because this aperture is uniform structure, so it will generate a uniform, almost uniform beam. Not scattering, but we call it diffraction. Because these diffracted from scattered from different points add coherently to generate one beam, and that beam is known as boundary diffraction wave. So this theory says that this diffraction pattern is formed due to interference of two beams. One is geometrical wave and second is boundary diffraction wave. I will further explain this phenomena in coming slides. So this is how the Fresnel-Kirchhoff theory explaining that this open aperture is not restricted by the aperture. Every point here serves as secondary source. These secondary wavelets interfere to generate diffraction pattern. And this is theory boundary diffraction wave. We say this is geometrical wave directly transmitting, and light interacts with the knife edge. It boundary diffraction wave. These interfere to generate the diffraction pattern. Okay. Now we have seen these type of images many times, like these bubbles, fringes in the bubbles, the butterfly, these different colors of the moorpunk. So why they are happening? So this actually involves both the phenomena, diffraction and interference of light, particularly when these microstructures are there, like this feather and this butterfly feathers, because they are microstructures. When light is incident on it, it gets deflected from these structures and they coherently add. Different color is provided because of angle of diffraction. It follows the diffraction conditions and dimensions of your structure. So what is interference? So interference is coherent superposition of light waves. Suppose we have two light waves, wave A and wave B, and it has some wavelength and frequency. So if they are coherent means their phase relationship is constant. They add, then we get the resultant intensity, and that may increase or decrease. So these are in phase, so resultant is increasing. We call it constructive interference. If they are out of phase, like this is up, this is down. So this is destructive interference, and resultant is intensity decreasing. These are examples of, say, two beam interference fringes, and this is the bubble. You can see different striking colors in the bubble. So interferometry is a technique which follows the principle of superposition to mutually coherent light waves. And in this case, generally both the beams are derived from a single source, because two independent sources is difficult to have coherent. It's a well-known technique for non-invasive quantitative measurements and precision measurements. Applications include refractive index change, small displacement, lens means optic testing, heat transfer, temperature studies, fluid flow studies, etc. So there are a lot of applications of interferometry. In photonics, also photonic crystals and these photonic components are being characterized using interferometry or holographic interferometry. That depends on the type of component. So let's just go through the basics of a wave. So a plane wave can be represented like that. EZT is traveling in the Z direction, and this is a linearly polarized wave. A cos kz minus omega t plus phi. Okay. A is complex amplitude, and this is k is your wave vector, which is direction of propagation. Omega is your angular frequency, phi is phase. And in complex representation, it can be written like that: A exponential after k z minus omega t. Generally, in our calculation, this frequency dependent, time dependent part we ignore, that is fluctuating so fast that most of the detectors are unable to catch it. So we are working most of the time with spatial component kz instead of temporal component omega t. But this also becomes important when we are, say, going for heterodynamic interferometry. Now in two beam interference, we have two beams representing in their distributions E1 and E2. Now it depends on type of beams, whether they are coherent beam or incoherent. According to that, total intensity will be defined. If they are incoherent beams, then individual intensity will be added. Total intensity I will be I1 plus I2, and we are unable to see the interference fringes. But in case of coherent light, amplitudes add, means E1 plus E2, and intensity is modulus square of amplitude. So if we open up this equation, it's I equal to A1 square, A2 square, A1, A2 star plus A1 star, A2. This star represents complex conjugate. So total intensity can be written like that, I1 plus I2 plus 2 I1 I2 cos del phi. Here actually this is the interference term, 2 square root of I1 I2 cos del phi, where I1 I2 square root represents amplitude modulation of the beams and cos phi defines the phase modulation. So this is important in many applications, whether we are amplitude modulating or phase modulating. Now coming back to diffraction. Now I will try to explain that is it really that diffraction pattern is two beam interference or boundary diffraction wave theory is same. For that we did this knife edge diffraction experiment. This is the knife edge which is illuminated by a point source, which is a diverging beam. We used a coherent light, helium laser source we used for this experiment. And in this observation plane, say illumination region, at any point P, two beams are coming according to this theory. One is direct beam, this is this R, this is A upon R exponent JKR. And second is light diffracted from this S, this is UD, boundary diffraction. And this is quite complex. It has cosine dependent on this angle of diffraction. And total field is defined by UG plus UD and intensity pattern mod square. So this is intensity scan along the knife diffraction pattern, and this is the light to shadow transition boundary. Means the left side is shadow region and right side is illuminated region. But as you know that due to diffraction process, shadow also not a sharp shadow. Some light is going to shadow region also. And these are fringes. So in our case, what we did, we expanded this fringe, we broadened this fringe to look inside it. Whether it can be used as an interferometric fringe. Can we study some phase objects there? For that, to achieve this, what we did, we moved this knife edge toward the focal point, this source S. Because this is the fringe width. Fringe width means this distance, width of the fringe, which is 2 lambda b square upon R to the square root n plus 1 square root minus n square root. And these are diffraction order. Lambda is wavelength. So as we, and R is this distance, this from source to knife edge. As we move towards the source, this distance R decreases. And if R decreases, fringe width increases. So we achieved this like that. We moved this, it is mounted on a precision stage, it's moved toward the source. And by this, we are able to get the infinite fringe mode. This was knife edge diffraction pattern. And see, three number of fringes are there. But when we reach close to the source, we call it infinite fringe width mode. Means fringe width become infinite. Only single fringe got the full field of view. So this is still a knife edge diffraction pattern, but position of knife edge we have changed. And we are trying to move that it's very close to the focus point. And in lens is genetic airy pattern. Airy pattern means these are circular fringes. In the center, we call airy disc, contains maximum light, 84% of total light. So that is used. If we diffract from that, diffracted light also has greater magnitude. So this is the experiment. Now we put a glass plate into test section. Means, I think I should first explain somewhere what is the test. This is like that. Collimated lens, another is focusing lens, then knife edge was there. After focusing to a diverging, so we put a knife edge there, like this one. So test section means before this, inside collimated, this region, before test section. So when a glass plate is inserted in the test section, we are able to see these interference fringes due to variation thickness of the glass plate. Now, as we know that if we block one beam, interference pattern should not be available. So we blocked light incident on this using a screen from this side. So contrast of this fringe is decreasing. From other side, now contrast this side is decreasing. But if you put screen both sides, so no interference fringe is visible. This glass slide is this one, but interference fringes are not visible because in this case, no geometrical light is available. Most of diffracted light is traveling there. And if you put the plate into whole beam, then also it's not visible because now this covers the whole region, so reference beam is not visible. Okay, so this proves that a knife has diffraction pattern is a two-beam interference phenomena. Now, why we are doing interferometry and Schlieren and all these techniques? For academic purpose is one thing that we have to understand the phenomena, that is the basic nature of a physicist. We should understand the phenomena. But we should do some applied things also, that why we are doing. So one of the main aim is phase visualization. Say something is not visible, it's available there but not visible. You want to see it. Because something say heat from a candle, or in this case, say this is heat is rising from the hand. So this heat is not visible with naked eye. To see it, we have to do something. And we can use following three techniques. One is shadowgraphy. Shadowgraphy means directly shadow you are observing of the object. It gives second derivative of the reflective index of density. Means very high density gradients only it can capture, like say shock waves or say edges of some glass plate. But smaller variation it cannot show. Second is Schlieren. Schlieren is in between shadowgraphy and interferometry. Means it gives first derivative of the reflective index of density. It's also not giving linear relations. Some density variations are there, so it can detect it. You can say intermediate level of disturbance it can detect. And another is interferometry. Interferometry is directly related. It gives reflectiveness or density direct relationship. It's linearly related. It's very sensitive. Now, difficulty of realizing the setup also increase. Shadowgraphy is very easy. You just put a light, put inside in front of light your object, you observe the shadow. In Schlieren, we need to put say knife edge, that will discuss what is that. And in interferometry, we have to generate two beams that will interfere to generate the interference process. So it's a vibration sensitive and more complex also. This is shadowgraphy. So this is a point light source. Some object is there. Schlieren is a German word. It means some say discontinuity in the middle. Once some Schlieren is there, some discontinuity is there, what it will do? It will reflect the light. And depending on the gradient of this discontinuity, light may be deflected at larger angles or smaller angles. So say if second order means high gradients are there, it will be deflected. And this is a bubble inside this test section. So light which was here in the center is deflected away, and now this becomes white light. Otherwise, it was uniform. This black fringe from where light has moved to the another section. This shadowgraphy. Now, another technique is Schlieren. Schlieren is more sensitive than shadowgraphy. So, in this case, what we are doing, we are using a knife edge and a lens or mirror, it may be any configuration. So, it forms image of the source. This source is imaged by the knife edge, and in the image source of the image, we put a knife edge which blocks this image. And depending upon blockage of the image, sensitivity depends. This is burning candle, and generally we are able to see this flame only. But this plume which is going away is not visible naked eye, but if you put a Schlieren system, it is visible. Similarly, in previous slide, I used this picture of hand. This is also visible by Schlieren system. It's very sensitive. Your hand is releasing heat, and Schlieren system is making it visible. Now, can we convert this Schlieren system into say interferometer? That is further work on this knife edge diffraction pattern what we carried out. So this is the case which I just explained how we tested is a two-beam interferometer. This was the focusing lens. This collimated beam is coming, and at the focal we put a knife edge. We arrange the knife edge such that it generates infinite fringe mode condition. And here we can say that there are two beams, as I told that boundary diffraction wave claims, boundary diffraction wave theory claims. One wave is geometrical wave, directly going without interacting with the knife edge. Another is diffracted wave is starting from the knife edge. These two interfere to generate the diffraction pattern. But in infinite fringe mode condition, when put a knife edge here, we are able to see the phase variations. And this is total intensity distribution. The UG is geometrical wave, UD diffraction wave plus 2C cos phi. C is this constant, which is directional dependent. So in this case, what we are doing, this is the focus of a focusing lens. So it's not a sharp focus. It generates some, we say, point spread function. A point cannot be imaged a point, but it will have some spread function. So this spread, say this was the point, but this is spread function. So it's not focused to single point, but chunky pattern. This is not airy pattern. And this central region known as airy disk, which contains around 84% of the total beam, which was total energy which was available in the collimated beam. And if you count up to say this second ring also, it will contain 92% of the light. And this is radius of the airy disk as 1.22 lambda f is the f number of the focusing optics. And its intensity distribution given by this relation. Because we are trying to diffract light from the airy disk so that our diffracted beam, bound diffraction wave has maximum amplitude so that it can generate high contrast in the fringes. This was a comparison. This soldering iron, where the air disk in conventional cylinder systems, the airy pattern is blocked so that it should not mask the information. But in our case, we diffracted light from the airy disk, so it behaves as an interference pattern. This is burning candle, and you can see these are interferometric fringes. But here only this half information is visible. This half information, this is symmetric. Burning candle is symmetric. So this half is lost. This is black portion here. Because we are using solid knife edge. So light reflected in this side was blocked by the knife edge. To get the complete information, a phase knife edge can be used. So in case of phase knife edge, light will be transmitted through it, and this is geometrical beam, and some light will get diffracted from there. So this is finite mode phase knife edge diffraction pattern. It is a pi/2 phase plate, so that change in boundary diffraction theory claims that there is a pi phase change of boundary diffraction wave with respect to geometrical wave. In geometric light to shadow transition boundary that we will discuss later. We are just contradicting that also with a few of our experiments. So it will generate 2 times stronger the boundary diffraction wave, and it will give full information. This side will also, it will transmit light, this side also. Light will be transmitted. And now this is the infinite fringe mode condition. This is solid knife edge, say razor blade. So that block this information was not reaching, and this is phase knife edge. So information both sides is visible. Another thing that you can use a mirror also, like a Lloyd mirror. Lloyd mirror interferometer is well known. From in that interferometer, we reflect light from the surface of the mirror, and the reflected light interfere with transmitted light to generate the interference fringes. Here, what we did, we used edge of the knife edge, this Lloyd mirror, as a knife edge. Instead of using knife edge, we just use mirror. Its edge is used to diffract the light, and its surface is used to reflect that light. So in this case also, we are able to double the amplitude of boundary diffraction wave in a simple way. Because it's easy to make a mirror as compared to make a phase plate. So it generated high contrast fringe like that. This was the conventional cylinder diffraction interferometer. and this is from the folding mirror slit diffraction, Lloyd mirror by use. This is photograph of the setup. This is helium neon laser, special filter. This is collimating lens. Then this is your phase object glass plate mounted here. Then condenser, focusing lens. This is the knife edge here or mirror edge, depending upon your cylinder diaphragm. And then we can observe directly, or we can use a CCD here, CMOS here to capture the results for quantification. So this is the case of Lloyd mirror. In a Lloyd mirror, this light, after focusing, we are putting Lloyd mirror. So light is striking on the mirror surface, get reflected, and it interferes with the directly transmitted light to generate interference fringes, like this one. This is the folded. Light is traveling in this direction, has been folded upon another portion of the same beam to generate these interference fringes, Lloyd mirror interference fringes, and fringes will be telling lambda d upon d. This capital D is distance between the mirror and your screen, and small d is fringe width of the fringes. So using these two concepts, concept of cylinder diffraction interferometer means knife edge, and concept of Lloyd mirror, we generated a new interferometer, and that we named diffraction Lloyd mirror interferometer. Means Lloyd mirror interferometer, but working on the diffracted light. So what we did, here we put a knife edge and align into infinite fringe mode condition, where only zero fringe is visible. Diffracted light is quite strong, and we put a Lloyd mirror on the diffracted light like this. This is diffracted light traveling all the directions, and we put a mirror which generates its image and light from this knife edge and reflected from this interfere to generate the interference fringes. And these are very striking interference fringes. And see, this left side is showing conventional Lloyd mirror interference fringes, which are inside this half circle only. But in case of diffraction Lloyd mirror, because we are using diffracted light, and diffracted light traveling in all the directions, so we are able to generate these fringes outside of this illuminated region, which in the shadow region also. Deep in the shadow region also you are able to generate these fringes. And now depending on orientation of your knife edge, you can generate fringe in this plane or in vertical plane, like this. So now region of interference fringes is increased. So for many applications, it is useful, say for your fringe projection techniques, where you are going for 3D shape measurement. So using this diffraction Lloyd mirror interferometer, we tried, because theory is saying that we cannot spread the geometrical part and boundary diffraction wave after diffracting interferometer. They are combined effect, you can say that this is a combined diffraction field, but you cannot separate into diffracted beam and geometric beam. But these our experiments clearly show that in this region there is no geometrical beam. So this region show that boundary diffraction wave is existing there, and we are able to generate the interference fringes boundary diffraction wave. Second, this experiment is used to show that boundary diffraction is traveling all the directions, though its amplitude depends on cosine function. It is not simple cosine, it's a very complicated function. So this was the case, light incident from here. This is knife edge, and we use Lloyd mirror in different conditions. Like this is forward plane, so in this case this is the Lloyd mirror condition. This is knife edge and Lloyd mirror. So we are able to get these in the directly transmitted forward direction. These interference fringes. Now with knife edge like this around 120 degree. So these are fringes in this region, but they are very weak. Digitally we have to enhance this to make it visible, but they are very weak. And we put a screen here, in the reflected light also we are able to generate these fringes. So these show that reflected light travels in the whole region. Now I was discussing something about pi phase change in light transmitting in geometrically illuminated and geometrical shadow region. To verify that, we perform another experiment on diffraction Lloyd mirror interferometer, and we put a screen here to block some portion of the light. This is the configuration diffraction lowered mirror. This is knife edge, then mirror, and we generated interference fringes like this. This is conventional lowered mirror. This is diffraction lowered mirror, and these fringes are generated. Now, what theory is saying that geometrical light to shadow transition means this boundary. This is shadow region. This is geometrically illuminated region. There is pi phase change of diffracted beam. It means at this boundary there must be discontinuity in the fringes. So to observe this, we use the screen to block the light. We block light from this side, so we are able to see that boundary diffraction generates straight fringes. There is no any change. There is no phase change any type of. Similarly, in this region also. So this experiment concludes that boundary diffraction is uniform. And uniform theory of boundary diffraction is very efficient. It was further translated into the geometrical theory of diffraction. Sir C.V. Raman also worked on it. He did major work in say 1946 and something there. But it was put on some mathematical background by Joseph Keller in a 1962 paper in JOSA A, where he defines that you can take diffracted light as a geometrical ray with some constant. And now that theory is very popular for solving various physical problems, say propagation of your signals from the antenna. So another experiment with diffraction lowered mirror interferometer, what we did, we generated in the single interferogram fringes of different shapes. Theory is saying that if there are two sources of light, say S and S dash, just separated by a distance of say S. Now, depending upon point of observation or direction of observation, different shapes of the fringes will be there. Generally, these are hyperbolic fringes, but if you observe in this direction, which is just bisector of these 2 points, you will get straight fringes. And if you observe in this direction, perpendicular to joining these two sources, you will observe circular fringes. And we generated all these fringes into single interferogram using the diffraction lowered mirror interferometer. So we aligned our mirror and knife edge such that diffracted light is available in say motion. This is the geometric light. So you can see that how much deep inside the shadow we are able to generate the diffraction fringes. Now this straight fringes correspond to this region. As you move away like this direction, and this is your now DC, and then it becomes curvature, and in this point it becomes circular fringes. So this is the only interferometer, say worldwide, which can generate all these shape of fringes into single interferometer. So this is very good for the education point of view. Using this interferometer, we can explain many things to the students in a visual fashion. Otherwise, we are generally using approximations to explain diffraction and interference, particularly diffraction of light. This is the photograph of the interferometer. We transferred this technology to an industry for commercialization. So this is a say diode laser, special filter, collimating lens, and condenser, knife edge, and then screen or some say sensor you can use there. And it's very simple to demonstrate many things. This same interferometer can be used as Schlieren instrument also for phase visualization. Now we will move towards types of interferometers. So there are many types of interferometers, and depending upon application, we have to choose which one is suitable for your application. So these are Rayleigh interferometer, Michelson interferometer, Twyman Green, Mach-Zehnder, Sennett, Fizeau, Meru, and holographic interferometers. So to start with Young's double slit interferometer. Actually, this is the first experiment performed in 1802 that conclusively demonstrated that light has wave nature. And it again depends on the diffraction of light. What Thomas Young did, he took the say sunlight or mercury light, then he filtered it. After that, this light is incident on the closely placed pinholes. Nowadays we are using slits, but that was a pinhole. It is separated by distance d. Now when light is incident on this pinhole, it gets diffracted like that. And size of this pinhole is such a small that diffracted light is, you will say, generate infinite fringe mode condition, means you are not able to see the individual fringes, you can see only diffracted light. Similarly, light diffracted from this another pinhole is also generating wavefront. These two now are serving as point sources of light, and they are coherent, so they interfere. And depending upon this condition of interference, it will decide where the fringe will be generated at particular location, it's dark or bright. And fringe width is again given by lambda d. D is this distance between the plane of pinholes to your optical screen, and small d is your fringe width. So this is the experiment. Still, this is used for many applications. In say quantum optics is very useful still, and say which way experiments that photon is traveling which slit. That is also one of the important experiment for studying dual nature of light. Based on that interferometer, Young's double slit interferometer, another Rayleigh interferometer was designed. And this is suitable for say to measure refractive index of gases or their densities. So there are two tubes. Light is passing through these two tubes, and then a lens is used to convert these. So these lenses actually superimpose these two beams, and in the superposition region we are getting the interference fringes. So this can be used for say as a refractometer to measure refractive index of mixture of gases or different types of gases. Similar interferometer is also used for astronomy, where mirrors are used to divert the beam in different directions, which is collected from the star, and then they are studying these interference fringes. Another classical interferometer is Michelson interferometer. So this interferometer conclusively ruled out the existence of ether, which was considered that ether is omnipresent, means everywhere ether is present. So in this case, this is source of light. They use an extended source of light, and a beam splitter was used to divide it into two parts. One beam traveling is a reflected beam, illuminating in one mirror, and get reflected back and go straight into this direction. The reflected part we are not worried about presently. Then transmitted beam is reflected by another mirror and then reflected by beam splitter. So this is now beam combiner also, combines two beams, this beam and this beam. And we are able to generate the interference fringes. Now, beam tilt to this mirror, you can generate either circular fringe or straight fringes. That you have to tweak with the mirrors. This has also many applications. It's used for the measurement of length or optical testing of components in optical soft testing, Fourier transform spectrometer, LIGO light, laser interferometer gravitational wave observatory, which is used for the detection of gravitational waves. In 2016, we detected first wave worldwide, which was detected the first wave. In India, it's INDIGO. So India is also working on LIGO, that's INDIGO. Optical coherence tomography and many other applications are there. This is modification of this Michelson interferometer. It's known as diamond green interferometer. And in this case, modification is that it's using a point source of light. Just at the focal point, means it's working with collimated beam. If it's collimated beam, now you are able to characterize many things. You are able to see testing of your various components, optical component with focal length, manufacturing defects, many things you can do it. So, say to measure this convex lens, this is reference beam, this is your object beam. A convex spherical mirror is positioned so that its center of curvature, this, coincides with the focus of the optic being tested. This is test lens. So applications are surface testing, flat surface, spherical surface. So this is used in optical soft testing. In this interferometer, when you are putting say some phase object, so light is traveling 2 times either from the object, and these beams are generally not well separated. So disturbance may travel from one beam, say vibrations or thermal disturbance. So Mach divide this interferometer, that he 2 beam splitters. One split into these 2 parts, which are specially traveling different directions. So in independent beam, you can put your test object, which will not affect the other beam. And you can compare this information of this beam, so object beam, with reference beam, which is detected by the detector. So this get reflected and transmitted, so it will generate a complementary fringe duration this also. Now you can record these fringes and you can analyze the various parameters of the test object, like heat transfer, temperature distribution, fluid flow, electro-optic modulators, holographic interference. So various things you can do that using this interferometer. So again, depending on application, say here you can see that these are separated, so vibration effect will be more. So more stability is required. But depending upon application, we have to select the interferometer. This Senec interferometer, actually this is a ring interferometer. In this light is traveling both paths. This travel like that circular path, and another reflected in this path. And they interfere here to generate the fringes. So this is common path interferometer. Coherent sources can be used here, and it's widely used for rotation sensing. Say gyroscopes are working on this principle. Gyroscopes are very important for rotation, say in your aircraft also. Next is piezo interferometer. What piezo did, that he used say diverging beam, and in the diverging beam he used a collimating lens, so it became collimated beam. This is test object. This is test object, and this is reference surface. So one beam gets reflected from the reference surface, and that is directed in this direction. Another is reflected with this test surface, which is also directed in this. These two interfere to generate the interference. And I think this is the widely commercialized interferometer for many applications. Say Zygo interferometer is also using this principle. By using this piezo mirrors, which can phase shift reference beam, these phase shifting interferograms are acquired for more precision quantification of the results. So in optical soft testing, this is widely used. Nowadays, this is also used in your industrial product testing in various industry for quality control. Another is Meru interferometer. So this is also a novel concept, and this is the say main thing is here. This is microscope objective such that a half mirror is inserted in between. The light is incident on it. This reflects it back, and another is traveling from there, which then reflected by the surface under test. These two, and this is PZT here to control phase shift. So this can be used in white light also, and this is also used white light interferometer or coherence correlation interferometer. This is widely used for surface topography measurements. Now, if your objects are say not transparent or not specularly reflective, in the all interferometers what we discussed now, either your object was transparent so light can go through it, or it is reflected specularly. But if you have an opaque object, then how to test it interferometrically? The interferometric test is highly precision test. So holography of first advantage here. So first I will briefly explain what is holography. So holography is a term combination of two Greek words. Holos means complete, gram means message, means which can convey complete message, then we call it hologram. It is a process of recording and display three-dimensional information without imaging optics. We don't need imaging optics to create a 3D image if we are using holographic concept. Therefore, holography opens up completely new possibilities in science, engineering, graphics, arts, entertainment, everywhere. So these are few of the photograph of holograms. This is the photograph of the experimental setup. Laser beam is coming, then it's divided in two parts. One is used to directly eliminate the recording material. This is known as reference beam. As interferometry, we are having two beams, reference beam and test beam. Similarly, here also we are having two beams. So this is a reference beam, which is directly coming on the recording material. Second light illuminates the object. We are using two beams here for proper illumination, but one can be used. That depends size and orientation of the object. So this diffuse object light will get scattered. Every point of this object will generate a spherical wavefront that will be diverging. The diverging wavefront is coming to the plate. In between, I will not using any imaging optics to form image of this object. These two interfere that we record and is known as a hologram. So this is the hologram which I think most of you have seen. This is a rainbow hologram and it's using the stickers. When you change angle, you see different colors there. Another, this is the left one is your reflection hologram. So these both works on white light. For recording, we need a laser, but for reconstruction, we can use white light. This works on the reflection hologram works on the condition Bragg diffraction condition. So light which satisfy the Bragg conditions will be reflected and we can see the hologram. And this bottom right picture show that one of the NDT, non-destructive testing. This is, you can see a cup, and in this cup there are these fringes, these are interferometric fringes. And along this line, there is discontinuity in the fringe. These fringes are of different shape and property, they are of different shape. And this is because along this line there was a micro crack in the cup, which is not visible by the naked eye, or if visible, you have to concentrate on it. But this technique that is shown, this is the problem. So this is holographic interferometry, because double exposure holographic interferometry. That I will explain. So how holographic work? So for that, briefly let I explain how photography is working. Because we relate holography with photography most of the time. So to record a photograph, we illuminate the object with a light, say flashlight of your camera, or say sunlight. Light get different scattered, and we use imaging optics to form image of this object on the recording material. And this became a photograph after development. If you see it mathematically, so this is the equation of the scattered beam. We call it object beam also. A naught exponential j phi. And what is phi? A naught is complex amplitude distribution, and amplitude distribution. Phi is phase distribution. Phase means 2 pi by lambda into optical path difference. Optical path difference means depth part. That what is depth between 2 points. So light traveling from the 2 points will acquire this much phase difference. Okay. So when we are recording photograph, all the detectors, including your eye, CCD, CMOS, whatever camera you are using, plates, are intensity sensitive, not phase sensitive, not amplitude sensitive. So they need intensity. So we convert this complex amplitude into intensity distribution, which is A naught into E naught star, which is complex conjugation. Now what is we are getting? This is A naught exponent j phi into A naught exponent minus j phi. Minus j phi means this conjugate. And this j phi minus j phi cancel out. What we have recorded is A naught scale. Only amplitude distribution scale, not phase. Phase part is lost. So in a photograph, we are unable to see the depth information. Only due to change in distribution of light scattered from different portions, we are able to recognize that this is the nose, this is the eye, this is the teeth. But actually, this is 2D information, not 3D information. So what we are doing in holography to get the 3D information? Actually, holography works on the principle of interference of light. So here we are using two beams. One is object beam, similar what we have used in our photography, and we add a coherent reference beam, Rx. Then we convert it into intensity, Rx, R square, O square, R star, O, and R O star. This is your object term. This means object wavefront, what is coming from the object as it is you are reproducing. And You can write it like that: OR cos phi r minus phi. This is phase modulation, this is amplitude modulation. So here, this phi term is not cancelled. It is retained in the form of interference fringes. And that's why holography provides three-dimensional information without imaging optics. So this is a recasted thing. This is your hologram after development. You eliminate with the reference beam. We call now it reconstruction beam. So it will generate all the four terms like R square, O square, R star O, and R O star. And this R is reconstruction beam. You are eliminating this R. So these become the four terms, and four terms means these two are say DC. One, this R into R square directly transmitting beam. R into O square. O square means interference of object beam with object beam itself, and say this is very randomly distributed, so it just can create a halo. So it's also generally concentrated around this one. Now third term is R square O, and R if you are taking a say plane beam, collimated beam, so you can count this is O. O means object beam. Your object was here, it was transmitting the beam, diverging beam like that. You just captured it. Now you are releasing. So we were traveling in this direction, the same direction you continue when you eliminate the reconstruction beam. So this, if you see from here, you will be able to see your actual object in 3D sitting. And this post or con plus conjugate. This was diverging beam, this is converging beam. It will generate image. This is conjugate image, but this is the real, because light is really focusing here. This is virtual image. So these are all four terms in the holography. So actually holography is a two-step process. First we record the hologram. During recording, we are using the process of interference of light. And during reconstruction, because during recording we have created thousands of gratings, because this object is so oriented that very complex grating pattern is there. The light is incident on that grating pattern, it gets diffracted, and by diffraction process, it forms an image. So this is the recording setup. This is your laser beam, divided into two parts. One is used to eliminate the object or scene. Second is reference beam, and you record on the film or plate whatever CCD, CMOS, what is available there. And depending upon material, we have to satisfy some conditions of recording setup also. After recording, you have to develop it, then it becomes a hologram. Now you put the hologram and illuminate with reference beam. You can see same reference beam, same angle, same divergence, same wavelength. You will be able to see the reconstructed image into 3D. And this is the condition due to which when you are observing speaker, you have to change angle to see the image, because unless this angle is satisfied of the original reference beam, you cannot see the reconstructed. So that's why you are tilting that hologram on a book or whatever to see its 3D information. Okay. Now holography can be divided into three types. One is conventional holography, what I just described now. So reference beam is there, object beam is conventional recording material is in the form of film or plate. We develop and then eliminate with the laser beam to see the reconstruction. Secondly, digital holography. In digital holography, this plate has been replaced with CCD. But this is not the only thing. Thing is that plates are having very high spatial resolutions. They can record 10,000 line pairs per millimeter. It means angle between reference and object beam can be very large. This angle defines the number of lines found, number of interference fringes found per unit area. But CCD and CMOS are having this defined pixel size, say 3 micron or 2 micron. So you cannot increase the angle arbitrarily. So generally we are using beam splitter, like in Mach Zehnder configuration, and a small angle is given by tilting it, so that these fringes can be resolved. Otherwise, this camera will not be able to resolve. You cannot record the hologram. During reconstruction, this process, you share in your computer, and then you reconstruct numerically into your PC. So you cannot see the visual hologram, but you can do various type of analysis, thermal studies or say NDTs, many things you can do in your PC itself. That is very important area. And third is computer generated hologram. In this case, you design your hologram to computer. In this case, you use laser, all the everything, and recording also. In this case, these laser and everything are there, recording your digital and reconstructing the computer. But in this hologram, you are designing into computer. And for reconstruction, either you need some printing techniques, or nowadays you can use special light modulator to see the image. So all these three are very important to further progress the hologram. But today I will be talking mostly on interferometry. So this is a slide about holographic facility at CSIU. We are having facilities for, say, recording of a conventional hologram. This is the hologram of Vijay Stambh of Chittorgarh. And we are having different types of lasers. We have digital holographic setup. We have conventional holographic setup. So we have good facilities there. Now coming to again back to interferometry. Now we have the knowledge of holography, that you can record three-dimensional information of diffuse objects using holography. Okay, so to test that object, whether some micro crack is there, or say this bonding with the materials is there, or you have say your photograph laminated, but after some time it get delaminated, so you can study these things. For that, generally three types of holography interferometry are there: double exposure, real time, and time average. I will explain one by one. And these are used for measurement of deformation, surface inhomogeneity, delamination, stress, strain measurement, shape or thickness measurement in different areas: aviation, automobile, biomedical applications, optomechanical testing, PCB testing. So many applications are there for holographic interferometry. MEMS testing also. Okay. So in real time holograph what's happening? These are real time holograms. So what is here? Now you make an experimental setup and record one hologram of the object. Now hologram is developed if it's conventional, or reconstructed if it's digital. Now replace your developed hologram in the same position, and again illuminate both the beams, open both the beams. So it will again, there will be a reference beam, there will be object beam, and in the direct beam there are two beams overlap. One is object beam reconstructed from the hologram, and second is object beam directly transmitted from the object. These two beams interfere to generate these fringes. Now, any change real time when you are disturbing the setup or disturbing the object, that disturbance will be reflected into these fringes. And in real time, you can see that where defect is there in the object, or how some process is evolving. Say mixing of say salt in water. So you can put the water and you can observe how that is mixing there. Second is double exposure holographic interferometry. So in this case, what we are doing, we put two exposures on the same hologram. It may be digital hologram or conventional hologram. So this is a recording material. This is object under test. So, and one reference beam is also added here. So first you record the object into one hologram. Then before second hologram, you disturb it. We call it loading. Means we put some pressure, it may be heat, maybe weight or any type of pressure. So the slightly micron level disturbance is created. And another hologram is recorded. Now in the plate there are two holograms. We develop this plate and illuminate with the reference beam. Because there are two holograms, so two wavefronts will be reconstructed like this. This one and this is another. And because you disturb the position, so these are slightly displaced, and that displacement results into interference fringes. So these are the equations. This is say first beam, second beam, then you can record, and this cosine interference fringes will be formed like this one. This is a bulb, incandescent bulb. So holograms were recorded. In the first case, it was for some time it was put on, so it became hot. We record put off, so that light of bulb is not coming to our plate. We recorded one hologram, wait for some time, it will cool down, record another hologram. and then reconstruct both simultaneously. We are able to see these fringes. These fringes show that how temperature is distributed inside the bulb. This is temperature distribution fringes. This is painting testing. Painting was delaminated at these points. So two exposures were made, one normal, another with some loading there. And due to that, see, these fringes are uniform, so it's no delamination. Lamination is okay, but at these regions, this film has been delaminated. So you can easily test it. Now this is also known as holographic non-destructive testing. This is another example. This is the replica of Konark bead, and two exposures were made. In between, some weight was put on it, and you can see the interference fringes, double exposure holographic interference fringes. And at this point, this frequency of the fringes changed suddenly. So along this line, there was a crack. So this can be observed. This can be testing for cracks. This is testing of PCB. We just powered it on and take holograms, and then you recast it. So if some heating is there, then more number of fringes will be generated in that region. Another interferometry is holographic real time, time average holography. Time average means this is generally used for vibrating objects, which are just continuously vibrating. Say sinusoidal vibration is there. So here we are giving a long exposure time. That's the time average. We are averaging 0 to t exposure time of the field. So this is the field which is averaged out, and it generates these fringes. Okay, so these fringes are means when it's vibrating at the extreme ends, it gives more time. So more exposure is received corresponding to that extreme edges, and that's why these fringes are. Using this study, the vibrations can be studied. This is widely used for, say, vibration of the engines, automobile engines, and type of other vibrations. Interferometers developed at CSIR. So using these techniques, we developed various types of interferometers, like Schlieren diffraction interferometer. And these Schlieren techniques, presently we are working for defense applications also. And when we worked for HAL for crashing measurement in, say, Sukhoi 30 aircraft canopy, after some time, some crashes means scratches are developed. It's not scratch, not crack, they call crashing. And it weakened the canopy, and many times blew off during flight. So we developed a technique based on to quantify that how much crashing is there and when you should replace it. For dynamic studies, also we are still working on that to study dynamic phenomena, which are very fast phenomena. We are still working on that. Diffraction Lloyd interferometer I explained in detail. Holographic optical based interferometer, various configurations we developed. Let's see. One of them is holographic steering interferometer, and then digital holographic camera for non-destructive testing applications. So this is one of the configurations of holographic HOE. H is holographic optical, where optics is replaced by holograms. In hologram, generally we capture image. Then we call it a hologram. If there is no image, just structured wavefronts are there, then holographic optical element. It can serve the purpose of grating, lens, mirror, or whatever. So here we recorded this H1 with two collimated. This reference beam was there, and these two collimated beams were here. Just focusing in this plane. When we recaptured this hologram, these are overlapping these regions. Put another plate H2 and recording it. Now we put both H1 and H2, eliminate this reference beam. It will recapture these two, and these will further recapture two from here. So this is directly transmitted, and one being reconstructed due to O1. So in this O1 plus 2, say, two beams are there, O1 plus O2, similar 2 are there, and we are able, if you put some object here, test object here, we'll get this interferometer. These are fringes, finite fringe mode and infinite fringe mode. Using this concept of HOE multiplexing, means various types of phenomena you can multiply, you can add into single hologram. We developed an HOE which can simultaneously be used for, we can use simultaneously realization of interferometry, Schlieren and shadow meters. So this is the construction of the HOA. Actually, these are two hollow lenses. This is a reference beam, and these are two focusing beams. So this is from one lens, this is another lens, and we expose it. After development, this is the HOE, holographic optical element. We illuminate with this beam. So this will be transmitted, and it will reconstruct these two beams. Focusing at these two points. These are focal length of these lenses. Now, if you put some test object here and put say knife edge here for cylinder applications and Lloyd mirror here for interferometry results, we can get all the results in a single exposure. Interferometry, shadowgraphy, and Schlieren. This is replaced. This is Schlieren, this is shadowgraphy. So these type of studies are very important when a large range of gradients is available. Say in plasmas. So plasmas have various level of gradients, and this is transient phenomena. What you represent at particular moment is not reproduced again. So such things are very important for such type of studies. Recently, we worked on shearing interferometer, holographic shearing interferometer. So I'll briefly explain what is shearing interferometer. There are various types of shearing interferometer, but we work on lateral shearing interferometer. And in shearing interferometer, generally like this. This is a shearing plate, shearing element we call. This is a parallel plate. Means both phases are parallel. When it's illuminated with collimated light, light will be reflected from front surface as well as from back surface. Two beams are there. One front surface reflected, second rear surface reflected. And due to this thickness, we are this traveling different path and get reflected. They are separated spatially. One beam is this one, another is this one. So this is shear. This much shearing is there. And this overlap region, interference fringes are generated. So this is known as shearing interference laterally, because they are laterally shifted. This is very simple. This is just plate and illuminated the collimated beam, you get the shearing. So this was initially proposed by M.V.R.K. Murthy, an Indian. So it's also known as Murthy interferometer. And for collimation testing, and this can be a wedge plate also. In case of wedge plate, fringes are there. And these fringes rotate depending upon characteristic of a beam. It's collimated, converging, or diverging. And this is represented by that this is your wavefront difference, and this is second wave derivative. Then, due to defocusing, this is defocusing term. And if you have tilt also, then you can put tilt term also. And using that, you can just, if no tilt is there, you get plane parallel plate. If tilt is there, you can get wedge plate interference fringes. And these are the results for collimation testing using this plane parallel plate interferometer or Murthy interferometer. So in case of plane parallel plate, when collimated beam is there, so because light reflected from both surfaces is collimated, so no interference fringes are generated. Only bright field is there. But if it's converging or diverging, in focus means diverging. In focus means your lens is towards your pinhole is towards the focus of the collimated lens. So this is diverging, this is converging. So for converging and diverging, we are unable to decide whether this is converging, this is diverging by looking at the fringes. And another problem is that when we achieve the first fringe, we don't know still it's infinite fringe mode or we can further go there. So how much collimation position we reach is difficult. In case of wedge plate, these fringes rotate. This is for diverging, it rotates say counterclockwise. In case of collimated beam, these become parallel to horizontal line, and in case of converging beam, it rotates clockwise. So you can quantify it, and you can tell direction also whether the beam is converging or diverging. We developed a compact holographic lateral shearing interferometer, and this is the interferometer. What we did, instead of having single plate, we use two holographic optical elements, 1 and 2. And these are recording in this setup. Two collimated beams are interfered at some desired angle. So this is generally the form of holographic gradient. Now these are two, so we put two simultaneously here, millimeter of the beam, and you get two recasted beam. They interfere to generate the fringes. Now you can by observing also you can say whether it is diverging, collimated or converging, or you can quantify for the processing these interferograms to get quantification and say what is the slope of the fringes. And the slope will tell how much divergence is there in the beam, quantity of beam. So this also enables us to test beams of different diameters. This is photograph of setup. Because according to theory, number of fringes 5 to 7 should be related in the interferogram. But if you change the diameter, number of fringes increases or decreases depending on condition. Because this number of fringes are controlled by wedge angle in the wedge plate. And once you make a wedge plate, that angle is fixed. You cannot change it. But here this wedge angle corresponds to this tilt between the holograms. So we put this H1 perpendicular and we give it tilt to H2. By giving tilt, we are able to maintain same number of fringes for different diameters from say 5 mm diameter to 35 mm diameter. And we accurately measured the collimation conditions. This interferometer is also suitable for coherence length measurement. Well, it's very simple. This incident beam is there. You just change separation between these two plates. As you change separation, this contrast will decrease. Highest contrast when they are in contact, near contact, and then it's decreasing. So these are line profiles, how contrast is decreasing. And we measure that this is with the Michelson interferometer, and this is using holographic serial interferometer. We have some less contrast. This is the contrast value, but trend is same. And this less contrast may be because this lot of noise is there, coherent light we used, and some dust particles are there. So that was giving noise. That's why this is reduced contrast. Now, I should also explain that how the fringes are processed. This is important part. So there are various techniques. I will just go through two main techniques. One is Fourier transform method. This is the interferogram which we acquired, and its intensity, as you know, is by A1 square, A2 square, A1, A2 star, and A1 star, A2. Now you Fourier transform this interferogram, and you will get its special frequency spectrum. Means in the focal plane, if you put a lens here physically, you will get in the focal plane 3 spots. But digitally, you will get in the focal plane like these spots. So this is DC. These two terms are there. Then this is A2, A1 star, and this is A1, A2 star. Now you can filter out any one of the order and further propagate, inverse Fourier transform it. You will get this wrapped phase fringes. Wrapped means this phase is going from 0 to 2 pi. From each 0, then again 2 pi, 0, again 2 pi like that. This is 0, this is 2 pi. Just I'm changing like that, it's varying. So to see actual velocity is increasing or decreasing, we have to go for phase unwrapping. So you unwrap this and you will get the how phase variations in there. And from there you can quantify your results. It may be 2D profile of thermal distribution or refractive index distribution or displacement measurement. Any parameter measure you can definitely. Or you can get slope also, say is collimation testing. This is a slab 3.6 -5, and this is by vertical. This is another technique which is phase shifting method. Sometimes it's not possible to get good results from the single interferogram. There may be so much noise or number of fringes may be insufficient. Then you have to change phase. As I told in visual interferometer, phase is changed. So this is a first interferometer 5. Then put change the reference of pi by 2. Phase of the reference is pi by 2. So if you know I will A minus B sin phi. Then again pi by 2, phi plus pi. A minus B cos phi. Again pi by 2, phi plus 3 pi by 2. Phi is this one. So A plus B sin phi. Now you can use this equation tan phi into I4 minus I2 from I3 minus I0. So you will get wrapped phase. And from there you can unwrap and get the variations. So these two techniques are widely used for processing of interferograms, for quantification of the results. That quantification is very much required. Now coming to last point, this is our recent development. As we know, in a holography there is a reference beam and an object beam, and reference and object beams are separated, so vibration is a problem. That's why we are having big vibration isolation tables, so that we can kill the vibrations. Now, digital holography is there, sensors are there, CCD or CMOS, they are quite fast. You can use pulse lasers also, or you can make some design which is very compact but efficient, so that you can make portable camera. This is used for various NDT applications. So what we did, we used a CMOS sensor, we used a very small diode laser, it's very small, say, around 1.5 inch only in length. And this is the configuration like that. This is diode laser, microphone objective, so diverging you put a leaf splitter. Here we put a neutral density filter to adjust the intensity of reflection object beam. This is limited the object. We used a diverging lens. This lens is used to reduce special frequency spectrum of the object. Otherwise, as I told in digital holography, CCD or CMOS sensor is having very less results. So it reduced actual size of the object, so it can be resolved by the sensor. But when you are using negative lens, it diverges the beam. So effective number of photons received by CCD is reduced, exposure time increases, and again vibration problem is there. To sort out that, we put another lens, converging lens. So now it collects that photons, and the number of photons are increased. So using this compact, we have this camera. Now you can see this tripod mounted. So it's portable digital holographic camera. Everything is fixed inside it, and you can use it for various applications. So here we have achieved 192% increase in the field of view using this configuration. And we recorded holograms on tripod mounted, on say ground placed, and in very lot of movement is there, still it's working, AC is on. So now it is ready for various applications. So this is the methodology that how we can process these holograms. In digital holography, we acquired two holograms, first in initial state of the object, second after loading, with thermal or any type of loading. Then numerically reconstruct both the holograms separately. We calculate phase of this one, say phi1, then phase from this one phi2, then filter region of interest in the reconstructed complex amplitude. Then numerically separate the complex amplitude, phi1 minus phi2 or whatever you reconstructed. You can get amplitude or you can get phase. You can get amplitude fringes, you can get phase fringes. So this is the benefit of digital holography. The complete field is available digitally with you. You can play, you can modulate phase, you can modulate amplitude, you can subtract phase, these things. So this is the added advantage of digital holography. So numerically reconstruct and devising, then unwrapping, and you can get 2D and 3D profiles for further your studies. So this is how your camera is working. These are few of the examples what we tested using this camera. These we put some indents, small holes or indents in the aluminum plate. And then we did thermal loading of the plate. And then we find out the dimensions.
Yeah, Dr. Rajkumar.
Yes, sir.
Yeah, I think we are running short of time now, and we need to wind up because there are students will like to interact with you.
Okay, sir. It's I think 1 hour to 5 more.
Okay.
It's almost over. Thank you, sir. So these are the profiles of the defects. Similarly, we put these press fit components. These are MS, this is aluminium, and we tested how this, if we heat it, how thermal distribution is there, and then how its dimensions are changing different directions. This camera is used for delamination testing of this polishing pad. This is used for fabrication of lenses, and it get demulated sometime. If you get delimited, the quality of the fabricated optics will be degraded. So using this we detected the delamination is there. With this, I complete my presentation, and presently we have been sanctioned a new project, dynamic holographic displays. Like this we have not done. This is from the internet, and report says holographic display market can replace televisions in our homes by 2023. But this may not be real, but we are progressing very fast. This world is progressing very fast in this direction. And for this project, we are hiring the manpower. We have almost 15 positions for different levels. So you can share with our students if they are interested. With this, I completed. Thank you for your attention.
Thank you, Rajkumar. You have given a very well understanding of the field of interferometry, and participants may have noticed that this field of interferometry, holography, is a vast field, and there is a lot of scope to do in this. And as you said that you are hiring the persons as well, so a large number of persons you will be hiring for this project. So this is a good opportunity for the researchers to join you. So by that time, I finally thank you. There are two questions. One is Nikhil. Nikhil, are you there? Nikhil?
Yes, sir. Yes, sir. Yes, sir.
Your question, you put your question yourself.
Sir, my question is meaning of 4 pi here in Laloid mirror, sir. Laloid mirror interferometry, sir.
Okay, so if we see in one plane, so how much maximum angle we can get? This is 2 pi. And in say orthogonal plane also we talk 2 pi in that plane. So 4 pi means whole space in all the directions diffracted light is traveling. It's
Sir,
just, if
we
you are using point
spherical.
Is clear?
Yeah.
If you are using say the focal point tip of optical fiber, so it can be seen illuminated from any direction. Means light deflected from the tip is traveling all the directions. It means
so one more question was from Nikhil. Which one is good for measurements between compact Michelson interferometer or big Michelson interferometer? You want to know the sensitivity, basically.
So actually this is a good question, and I think most of the people have learned about LIGO.
Yeah.
I have just briefly that because LIGO needs very high sensitivity, and very high sensitivity means a small displacement of say one of the mirrors or change in optical path you have to test. If you magnify the change, it means you have to go for a longer distance. Only then you can see the change. So longer the path length, it has say 4 kilometer 1B in the LIGO. That's why this is more sensitive. So larger, more sensitive.
Larger is the more sensitive. Okay, good. So one more question from Alok Kumar Gupta. Alok, are you there? Alok?
Yes, sir. Yes, sir.
Okay. Your question is, are shadowgraphy and Schillerian methods quantitative phase techniques?
Yes, sir. Yes, sir.
Yeah.
Okay. So now it depends upon the application, what application we are doing.
Yes.
Most of the time, Schillerian and shadowgraphy has qualitative nature for most of the applications. But nowadays, there are few techniques because Schillerian is having so many variations. So quantitative Schillerian is also available. So depending on application and configuration, it may be quantitative.
Okay, sir. Actually, Miss, I'm working in the quantitative phase, Miss method, and sir, I have not seen much, Miss nowadays these shadow and Schillerian method. So, Miss, what are the reasons? Nowadays, there are some other method Miss holography and
Right?
yes.
Interferometry, holography is only you are able to see, but not shadowgraphy and Schillerian.
Yes, sure.
Yeah. So actually, these are crude techniques. shadowgraphy and cylinder are generally crude technique. They are more suitable for visualization, but they are generally used for wide field of view. Say you want to test your models of your new aircraft. So wind tunnels are there. In India, we have many wind tunnels. Some are with ISRO, then in CSIR, NAL, National Aeronautics Laboratory, Bangalore, we have 4 or 5 wind tunnels. So wind tunnels have cylindrical system. Design is put in the wind tunnel, then wind is there, and how your design is interacting with the wind, means aerodynamic studies. That is visualized using cylindrical system. So these are some commercial systems, but in research level, one is background oriented steering. So when people are working on that worldwide, background oriented steering, that gives you almost infinite field of view.
Okay. Okay. I
Okay.
think there are no more questions. So I thank you,
Thank you very much, sir.
for giving a very good presentation on interferometry, telling about the scope of interferometry, and there is a lot to go ahead with your 3D project on holography. So I wish you good luck and have a nice time. All the participants, tomorrow we'll be meeting at, as usual, at 9:55. Tomorrow is a talk by Dr. Naresh Chand, again from USA, but that will be a total light talk. It may not be technical, but it is art and science. Basically, a spiritual talk will be there. So it will be a good one. So, okay.
Okay, thank you.
Each one, everyone.